Hello everybody, I'm Vincent Martin from the Computer Science Lab of Bordeaux in France, and I will present to you my work on using reading mistakes as features for sleepiness detection in speech. Sleepiness is a public healthcare problem as it impacts everyday life of those who suffer from sleepiness diseases, altering their quality of life and being responsible for numerous road accidents. Patients with such chronic diseases need a regular follow-up with their doctor, which is quite difficult because of the increasing queuing in sleep clinics. Moreover, such interviews don't allow physicians to embrace the patient response to treatment when they are at home. To tackle this issue, we have developed a virtual physician that has been tested and approved by the patient. The aim of our project is to collect the voice of the patient when it is interacting with the virtual physician to estimate its sleepiness level. The task of sleepiness detection through voice has already been studied across Interspeech 2011 and 2019 challenges. Our work gives novelty on this problem by using several measures of sleepiness. We measure both objective by EEG and subjective sleepiness, whereas the databases of the state-of-the-art are only labeled with subjective sleepiness. Moreover, contrary to previous works based on healthy subjects, we work with patients that are suspected of having sleepiness diseases from whom the subjective and objective sleepiness may not correlate. Finally, most of the classification systems of the state-of-the-art are based on voice quality features that are mainly measures of neuromotor processes. We introduce here reading errors as features of sleepiness, depicting the impact of sleepiness over cognitive processes. In this presentation, I will attempt to answer the main question: are reading mistakes relevant for sleepiness detection, and if they are, for what type of sleepiness? This leads to three sub-problems. First, we need to define which mistakes we should take into account. Second, the labeling of this error led to the exclusion of some speakers of our database, so we elaborated some exclusion criteria to differentiate the errors due to the influence of speech or motor pathologies and those that are due to sleepiness. To answer all these questions, we based our study on the MSLT database that I will present to you right now. The MSLT corpus is based on the recordings of 105 patients suspected of having a sleep disease and taking a multiple sleepiness latency test for diagnosis or control. The MSLT consists of 5 naps every 2 hours since 9 a.m., during which the patients are asked to sleep, contrary to the usual maintenance of wakefulness tests used in other researches. They have a maximum 20 minutes to fall asleep, and the MSLT iteration value is a sleep onset measured by EEG. As a consequence, this value is comprised between 0 and 20 minutes, and the mean of the MSLT iteration value across the naps is the medical criteria to assess narcolepsy and other sleep pathologies. We kept the medical limit of 8 minutes to differentiate sleepy speakers from non-sleepy speakers and used this mean MSLT value as an objective sleepiness measure. Before each nap, the patient are recorded reading a text and they fill a subjective sleepiness questionnaire, the Karolinska Sleepiness Scale, the same test that is used in the state-of-the-art databases. The read texts are different across the naps, but the same for each iteration of the test. There are approximately 200 words extract of Le Petit Prince, leading to recordings between 1 and 1.5 minutes. One of the advantages of the database relies in the fact that we have both the audio and the corresponding exact transcription, so we can count and identify reading mistakes and label the database with them. So we unlabeled the MSLT corpus with 5 types of errors to ensure that each one is at the same time specific of a process and enough observed to be used as sleepiness marker. These errors have been defined with the help of speech therapy students. The first type of error is stumbling, which are linked to the assembling capacity of the reader. Assembling is the process of deciphering a word between reading it out aloud, and interferences with the assembling process manifest themselves by hesitation within a word, too long sustain of vowels in a word, or word or fragment of sentence that are repeated. The opposite of assembling reading is addressing, that is the fact to read a word wholly without deciphering the syllables one by one. Errors in the addressing process, that we labeled as paralexia, include the interchange of syllables or collapsing, for example. We also labeled the addition or deletion of one or multiple words, and the syntactic reversal, that is the inversion of two or more words in a sentence. If the reader corrects himself after an addition, deletion, paralexia, or syntactic reversal, even if a fragment of sentence is repeated, no supplementary stumblings are counted. While labeling the corpus, we noticed that a few patients made a lot more mistakes than majority. Discussing with speech therapists, we have found that this patient had pathologies or sequelae of pathologies that can affect their reading and speaking capacities. As a consequence, we excluded the speakers from the database. If this has the consequences to reduce the number of speakers in an already small database, we ensure that the observed errors are linked to sleepiness, not pathologies. We have drafted 4 main profiles of speakers that do not have a sufficient reading level due to a pathology. First, we identified 3 speakers with alexia and visual-attentional deficit that have been found to have medical history of stroke or ischemic attack. Second, 3 patients presenting articulatory deficit or uncommon voice have been proven to have neuromuscular diseases such as dysphonia, myotonia, and epilepsy. We did not observe the case, but we advise to also exclude patients that have any other types of neuromuscular disease, chorea for example. Third, 3 patients skipped lines or too many words that have been identified as consequences of attention deficit. Finally, we excluded 4 patients presenting characteristics of stuttering, cluttering, dyslexia, or any other disorder implying the deciphering of the text. 1 supplementary patient suffering from serious inflammatory diseases and not presenting a sufficient level of reading has been excluded. Thus, we excluded a total number of 14 patients. The study is based on the 91 remaining subjects divided into 23 sleepy speakers and 68 non-sleepy speakers. Now that we have a clean database, we begin by observing the distribution of each type of errors in sleepy and non-sleepy patients. This is what is represented in this figure. For each type of error, we have represented the mean number of errors per patient on the 23 sleepy ones in blue, the 68 non-sleepy ones in sea green, and the 91 total speakers in orange. We computed bandwidth tests between sleepy and non-sleepy to show the significant difference between distribution. These tests are represented by stars on the graph. We can first observe that independently of the type of errors, the total number of errors is higher for sleepy subjects than for the non-sleepy ones. If the first makes an average of 25 mistakes during the 5 nights, the latter makes less than 17 mistakes in the same time. This difference is observed on all the types of errors, excepting syntactic reversals, which are not enough observed to be of interest, less than 1 observation per patient in average. As a consequence, we did not keep this type of error for the following discussions. Now that we have observed that there are differences between sleepy and non-sleepy speakers, we study the correlation between the total number of errors of each category per patient with their age, social level, mean MSLT value, and mean KSS value. We don't observe correlation neither between reading errors and age, nor between reading errors and social level. The total number of stumblings and deletions don't seem to correlate with sleepiness. On the contrary, the total number of additions per patient correlates with mean MSLT, and the total number of parallaxia per patient correlates with both mean MSLT and mean KSS. Consequently, additions seem specific of objective sleepiness, whereas parallaxia is sensible to both types of sleepiness. To complete this observation, we want to see if there are a link between the variations of errors and the variation of sleepiness across the naps of the test. The variation of parallaxia and addition compared to the variations of MSLT value across the 5 naps of the test are represented in this figure. These graphs have common points, such as the hollow at the third nap, for example, that can be due to the fact that patients take their lunch few minutes before the test, or the conjoint augmentation of MSLT value and error production during the last nap that can be due to the boredom or the fatigue that the patient expressed during the 5th iteration. Moreover, the different texts read during the naps are not totally equivalent in terms of difficulty or number of dialogues. To distinguish the influence of the iteration and the text and the objective and subjective sleepiness and the variations of the errors, we conduct a multivariate ANOVA with repeated measure. The results of the statistical test are represented in this table. Concerning the additions, the intersubject variation are due to the MSLT, while the intra-subject variation are linked to the KSS. This means that the differences between subjects are explained by differences in MSLT, whereas if we take a subject and observe the variation of its additions, the fluctuations are explained by the variations of KSS. The same observation can be made for parallaxia and sleepy subjects, except that the intra-subject variation are not only due to the variation of KSS, but also iteration or text effects. Concerning dilations, only the intra-subject variations are linked to iteration factors, and variation of stumblings are not linked to anything. These types of errors does not seem useful for our problem. To conclude, we have elaborated reading errors measurements that are linked to both the subjective and subjective sleepiness states of the speakers. Inter-subject variations of additions have proven to be a relevant marker of objective sleepiness, whereas intra-subject variations of additions and parallaxia are markers of subjective sleepiness. Our future works include the elaboration of a system to automatically detect these errors using automatic speech recognition, and the fusion between vocal features and reading errors to enhance classification accuracy that is only 61.5% considering only the reading errors. Thank you for your attention. If you have questions, I will be delighted to answer them.